This is a quick guide to solving exponential equations. Now, the first case is perhaps the most simple. Whenever we solve exponential equations, what we're trying to do is, first off, we're trying to get our bases to match. So this is always the first step. We're always trying to get the bases to match if they don't already match. After the bases match, we can set the exponents to match. So the basic philosophy here is we can say if the bases match, so must the exponents. At this point, we can solve an equation. But the key part is we need to make sure the bases match first and foremost. A simple case would be something like this. 3 to the x equals 3 to the second power. The bases already match. They're already 3's. So we can say the exponents match, which means x equals 2. Now, something that would be a little bit higher up would be something like this. 2 to the 5th equals 2 to the 5x minus 3. The 2's already match, meaning our bases match. So now we can just set the exponents equal to each other. We can say 5 equals 5x minus 3. To solve this, we add 3 to both sides. So we get 5x equals 8. Divide by 5. Now we can say x equals 8 over 5. Or we can say 1 3/5 or 1.6. It doesn't matter as long as you have one of these three answers. Now, what happens when the bases don't match in a situation like this, for example? 100 to the 7x minus 1 equals 10 to the 3x plus 3. Now, in this case, the bases don't match. One's 100 and one's 3. So, since we have that happening, we need to somehow make sure the bases do match. Now, we know that 10 to the second power gives us 100. So instead of 100, we're actually going to rewrite this as 10 squared raised to the 7x minus 1 equals 10 to the 3x plus 3. Now, we're raising a power to a power here. So what we really have is 2 times 7x minus 1 equals 3x plus 3. We can now set the exponents equal to each other because the bases match. So we get 14x minus 2 equals 3x plus 3, and this is distributive property. We want to move the x's to one side, so we're going to subtract 3x from both sides and the numbers to the other side. So now we can say 11x equals 5. To solve this, divide by 11. X equals 5 over 11. Now, the next case, we have to do a little bit more work for. The last problem, bases were obviously 10. In this problem, the bases are totally different. We have a 9 and a 27. We can't rewrite 27 using a 9, and vice versa. We can't rewrite a 9 using 27. So what we have here is we need to look at their common terms. In this case, 3 to the second gives us 9. 3 to the third equals 27. So instead of 9, I'm writing 3 to the second. Instead of 27, I'm writing 3 to the third. We multiply our exponents, so we get 4x equals, remember, use distributive property here. We're taking that 3 and distributing it to both the x and the negative 1. 3x minus 3. Subtract 3x from both sides. X equals negative 3. Now, in the second case, we do not have common bases. There's no possible way to rewrite them in terms of each other. So an example of this would be something like 8 to the x power equals 20. We can't rewrite an 8 in terms of any common terms. 2 doesn't work. 4 doesn't work. So we're a little bit stuck here. Now, really what I'm about to show you is a proof for the change of base formula, which is the following. Log base b of a equals log of a over the log of b. So this is really just a proof for that formula. Here's what we're going to do. We're going to take the log or ln, it does not matter which, of both sides. So we take the log of both sides. Now any exponent that we have gets moved using property 3 of exponents. So we get x log of 8 equals log of 20. To solve this, we really have multiplication going on between the x and the log of 8. So we divide by log 8 on both sides. So we get our answer, x equals log of 20 over log of 8. Now using a calculator, what we're going to do is we're going to take 20 log divided by 8 log equals 1.44. So now we can say that x equals approximately 1.441. Now, if we have anything else besides just an x in the exponent, it gets a little bit complicated like this. 7 times 7 raised to the 3x equals 18. We can take the log of both sides. So we get log base 7 of 3x equals, log of 3x, log of 7 raised to the 3x equals log of 18. 3x gets moved to the front. So we get 3x times log of 7 equals log of 18. Now in this case, we are dividing because there is multiplication going on between all three terms. But we want only an x here at the very end. So we're dividing by a 3 and a log of 7. So we have log of 18 over 3 log of 7. Now if we're going to use a calculator on this, what we're doing here is we need to make sure we use our parentheses. First, we want the log of 18 divided by, open your parentheses, so we have 3 times 7 log, close the parentheses, now equals. So our final answer is actually x equals 0.495, and it's actually approximately 0.495. It's hard to define because of all the decimal places we have here. Now, another easy problem would be something like this. 4e to the 2x minus 2 equals 15. The first thing we do is add 2 to both sides. We're trying to get the base and the exponent alone on one side before we even start solving this. So we get 4e to the 2x equals 17. Now, since there's multiplication here, we divide by 4 on both sides. So we have e to the 2x equals 17 over 4. Now, normally we would solve this with log, but whenever we have this, I always actually recommend using ln, which we could have done this whole time. So we're going to take the ln of each side. Now the reason I say we're going to use ln in this case is because whenever we use ln, it's actually base e, even though we don't say anything. So now what we have is 2x equals ln of 17 over 4. To solve this, divide by 2. So if we use a calculator, we get ln x equals ln of 17 over 4 divide by 2. Using a calculator, what we would do first is we'd put in 17 divided by 4, close a parenthesis, or equals, take the ln of it, and then we're taking that and dividing by 2. And we get 0.723. So now we can say x equals 0.723.